Welcome to Lecture 2, Causal Hygiene Designing for Reason. Last time we established that software design is fundamentally about preserving causality. The ability to reason about how actions lead to consequences is what separates maintainable systems from unmaintainable ones. We diagnose the problems, hidden dependencies, global state, implicit side effects, and tangled time all destroy our ability to reason locally. They force us to hold more in our heads than cognitive limits apply. Today's question: how do we preserve causality as systems grow? The answer isn't in specific technologies or frameworks, it's in understanding the principles that make causality explicit and the architectural patterns that contain it. So, there are four principles that preserve causality. These are not stylistic preferences, these are the necessities that emerge from the constraints of human reasoning and the nature of causality itself. The first is locality, that is, effects stay near their causes. Now, when you modify a system, the impact should be concentrated near the function, not scattered across the system, not hidden in distant modules. Locality reduces cognitive load. You can understand the change by examining a small region of code. You don't need to traverse the entire code base to predict consequences. Now, violation of these is typically things like global state, event buses without clear boundaries, and shared mutable objects that pass through many layers. The second is explicitness, which is dependencies are visible. If function A depends on B, that dependency should be in the code you're reading, not discovered at runtime, not buried in framework magic, not implicit in execution order. Explicitness means mental model building. You can see the causal graph by reading the code. Dependencies are in signatures, in imports, in explicit parameters. Now, typical violations are things like service locators, implicit context, that includes thread locals and globals, ambient authority, dependency injection containers that hide what depends on what. The third is unidirectionality. Now, causality should form a directed acyclic graph. A causes B causes C, not A causes B causes A. No cycles. Now, cycles make reasoning impossible. To understand A, you must understand B. To understand B, you must understand A. You're trapped in circular logic. You can't find a starting point for local reasoning. Typical violations are two-way data binding, circular module dependencies, callbacks that modify their callers, and objects that know too much about their containers. The fourth is about immutability. When you read a value, that value shouldn't change behind your back. When you pass data to a function, that function shouldn't modify what you passed. Immutability reduces the state spaces you must reason about. You don't need to track who might modify what, when. You don't need to defensive copy. Past causes remain stable, so tracing effects backwards is straightforward. Typical violations are shared mutable state, objects modified after construction, function parameters mutated inside the functions. Now, these aren't arbitrary rules, they emerge from how reasoning works. Locality works because working memory is limited. Explicitness works because we build mental models from what we can see. Unidirectionality works because we reason causally forward and backward, not in cycles. And immutability works because tracking changing state explodes cognitive complexity. Now, every violation of these principles makes the system harder to reason about. And harder to reason about here isn't subjective, it's measurable in time to understand, confidence in changes, and defect rates. Now, let's examine how these principles manifest in architecture. Now, every successful architecture pattern is a strategy for preserving causality. Let's start with boundaries and contracts. The function signature is the simplest causal contract. Inputs go in, outputs come out. If the signature is honest, if it declares all dependencies and all effects, you can reason locally. Now look at the calculate price method over here. This is transparent causality. Everything that affects the price is visible in the signature. Now contrast this with the calculate price, which takes the product ID and returns the price. That would be opaque. What does it depend on? Or what else does it depend on? You can't know without reading the implementation. So the principle here is make dependencies parameters and make effects return values. Push hidden state into explicit parameters and eliminate ambient dependencies. Now, interfaces work the same way at module boundaries. An interface is a causal firewall. It declares what crosses the boundary and hides everything else. You can reason about code using the interface without understanding implementation detail. But this only works if the interface is honest. If the interface says, I take X and return Y, but actually also modifies the global state Z, the firewall has holes and causality leaks through it. Now, there's another thing called separation of concerns, which is used very frequently, and it's usually explained as organizing code by responsibility. But the deeper principle is causal separation. That is, you are ensuring that different causal chains don't entangle. Now, let's talk about a couple of patterns where you have separation of concerns. First is the command query responsibility segregation pattern. Here, queries read state and commands modify state, never both. Now, if you think about the reason why this should be the case, because when a function both reads and modifies, you can't reason about it without understanding both the current state and how the state will change. The causal dependencies are forming a knot over here. And when you separate them, then queries have simpler causality, state leading to a result, and commands have simple causality as well. That is, the input leads to a state change. You can reason about these independently. Let's look at event sourcing. That's causality as history. Traditional databases store current state. Event sources stores the sequence of events that lead to that state. Every state change is recorded as an immutable event. Now, why does this help causality? Because you're making the causal history explicit and permanent. Want to know why this field has this value? You just replay the events. The entire causal chain is preserved. Event sourcing also enforces immutability and unidirectionality. Events are facts about the past. They don't change. They only flow forward in time. Let's look at bounded context in domain-driven designs. DDD's bounded contexts are causal isolation zones. Within a context, you have your own models, your own rules, your own causality. Contexts communicate through explicit interfaces at boundaries. This is locality at architectural scale. To understand behavior within a context, you only need to understand that context. The causal graph doesn't exist beyond the boundary. When contexts are poorly defined, you get shared models that mean different things in different parts of the system. Changes to the model create ripple effects across contexts, and causality then spreads uncontrollably. Let's also look at the functional core and the imperative shell pattern. The pattern is that you isolate pure logic, which is the functional core, from side effects, which is the imperative shell. The core contains all business logic as pure functions. Same inputs always produce same outputs. No hidden dependencies, no side effects, pure causality. The shell handles I/O, state, external systems. It calls the core, gets results, and applies effects. Now, why does this work? Because you've separated the complex causality, that is business logic with many interacting rules, from the unpredictable causality, that is external systems, timing, failures, etc. You can reason about the core mathematically. You can test it trivially. The shell is thin and obvious. Now, notice what all of these patterns have in common. They make causality explicit and contained. CQRS separates causal chains so that they don't interfere. Event sourcing makes causal history permanent and visible. Bounded contexts prevent causal sprawl across boundaries, and functional core isolates pure causality from effectful causality. Now, these patterns persist not because they're fashionable, but because they solve the causality problem. When you adopt them blindly without understanding this, you get the structure without the benefit. You have the pattern, but not the clarity. Now, the goal isn't to follow patterns, the goal is to make causality transparent. Patterns are tools that help when applied with understanding. Now, let's talk about the hard part. What happens when systems span networks and time? Now, distribution fundamentally complicates causality. In a single process, causality is clear. Function A calls function B, which calls function C. The call stack is the causal chain. But across services, causality becomes ambiguous. Service A sends a message, service B receives it eventually, maybe, unless the network fails, or the service is down, or the message is duplicated, or it arrives out of order. Now, let's talk about why microservices make causality harder. Now, microservices are appealing because they promise isolation. Each service owns its domain, bounded context made explicit. But they introduce distributed causality. A user action triggers a cascade of service calls. Service A calls B, calls C. Each call crosses a network. Each network hop adds latency, failure modes, and ordering ambiguity. The causal chain, which was a function call stack, is now an asynchronous message chain across unreliable networks. You can't trace it by reading code. You need distributed tracing. You need correlation IDs. You need to reconstruct causality from logs. And here's the deeper problem. Distributed systems have no global clock. Service A and service B don't agree on now. When two events happen in different services, their causal ordering might be ambiguous. Did A cause B, or did B cause A, or did they happen independently? This isn't a tooling problem, this is a fundamental physics. The CAP theorem and FLP impossibility results are theorems about causality under distribution. They tell us there are limits to what we know about distributed causality. Now, what do we do about it? The first thing is to minimize distribution. Don't use microservices for causal isolation when a modular monolith would work. Distribution should be the last resort, not the first choice. When must you distribute? If you want to make causality explicit in your protocols. Use correlation IDs, use causal ordering mechanisms like vector clocks or logical timestamps, and build your system so the causal chain can be reconstructed. Use bounded context rigorously. Each service should be causally autonomous. It should need synchronous calls to other services to process a request. Eventual consistency and asynchronous messaging reduce causal coupling. Now you have to embrace observability as causal forensics. You can't reason about distributed systems the way you reason about local code. You need tools to reconstruct causality after the fact. Distributed tracing, structured logging, metrics. These are the tools for making the invisible visible. And fourth, accept the trade-offs explicitly. Distribution trades causal clarity for other properties. Scale, fault isolation, independent deployment. Make this trade consciously. Don't distribute for organizational convenience and then wonder why reasoning became impossible. Now, the fundamental tension is between distribution versus comprehension. The more you distribute, the harder causality becomes to trace. Now, this isn't a problem to solve, it's a constraint to work with. Designed with this constraint in mind, when you must distribute, build in the mechanisms to reconstruct causality. When you don't need to distribute, don't. Now, in closing, I'll say that causal hygiene isn't a one-time activity, it's continuous discipline. Every design decision either preserves or erodes causality. Every abstraction either clarifies or obscures the causal graph. Every dependency either strengthens or weakens your ability to reason. The principles we covered, locality, explicitness, unidirectionality, and immutability, aren't rigid rules. They're guidelines that emerge from cognitive constraints and the nature of causality. Follow them when they serve clarity. Break them consciously when you must, but understand the cost. The patterns we examined, from function signatures to bounded contexts, are strategies that have been proven effective at constraining causality. Use them not because they're best practices, but because you understand what causal problems they solve. Now, in the next lecture, we'll talk about the hard cases. What happens when causality involves time and concurrency? How do we inherit systems where causality is already broken? How do organizations and tools shape the causal structure we create? We'll explore the limits of causal reasoning and what it means to make causality our organizing principle.